Thank you so much for the invitation and the nice introduction. And I was told that the audience was going to be quite wide in background, and so I hope my talk is going to be accessible to everybody. Please feel free to ask me questions at any time. And for the technical parts behind some of the things that I'm going to talk about, I'm going to be here, for the whole evening. And so if you have questions after the talk, those are very welcome. So I like to work on a variety of data sets coming from many different applications. Some of the ones that will appear in the talk are hyperspectral images and movies. These are images where at every pixel, instead of having just 3 colors RGB, you measure tens or even hundreds of colors in different frequencies of light, so that you have sort of access to the chemical information at every pixel. And you can think of such an image as a high-dimensional data set where every point is a pixel, which is now a high-dimensional vector of photon counts in different frequency bands. And those are used in a wide variety of applications, from agriculture to medicine to military applications. Other data sets that will appear in the talk come from molecular dynamics, where people run long molecular dynamic simulations. And every vector there is composed of the coordinates of all the atoms in a molecule. So if a molecule has n atoms, you have the 3 n coordinates of that molecule, if you're working in state space. And the n can be very large, easily hundreds, thousands, millions. And so you collect all this data, you have all these long trajectories, and then you would like to understand some properties of the large time behavior of these molecules. And in particular, what are the states where the molecule spends a lot of time and how it transitions between these states. And I do work also on networks and graphs. I will not be talking about those today, but it's something that I find it really interesting, and in particular, how to do harmonic analysis on such discrete structures. Here is a very short movie coming from molecular dynamics for a small peptide. And just to give you an example of the quantities that are involved. So the dimension is 3 times the number of atoms, easily hundreds of thousands or millions. These simulations are run with very teeny time steps, so the scale of femtoseconds, that's 10 to the minus 12 seconds. Unfortunately, the events that we're interested in happen depending on the event and the molecule and so on, at a completely different time scale, at the scale of a millisecond or even of a second. And so in order to witness even one of those events, you have to run extremely long simulations. There is a large separation of time scales here. And so the data sets have to be very large, contain a lot of configurations of these molecules coming from very long simulations. And if you want to do statistics of these rare events, clearly the amount of data is just staggering. Other types of documents of a completely different type could be text documents. I think Google is going to finish scanning all the books in the world in a few years. And we're going to have 130 million books. And you can ask many questions about how we are going to use all those text documents. Clearly, Google is going to provide a way of searching through them, but there is so much more information than just searching for keywords in those documents. And in general, I'm interested in looking at very different data sets, but sort of designing algorithms that allows us to extract useful information and that work regardless of the type of data that we're talking about. And it is surprising to me that there is common mathematics that can be done across very different data types. So the outline for the talk is probably too ambitious, but I plan to go at least through the first 2 points. The first point is something that many of you might have already seen. I call them global geometric models for data, where you have a large data set and you try to understand the global large-scale geometry of that data. And at the same time, we will be talking about issues about the dimensionality of the data. Data is very high-dimensional. There is a so-called curse of dimensionality that I'm going to briefly mention. There are many ways of trying to go around this curse of dimensionality, and the way that we will consider in this talk and discuss in this talk is when the data is, yes, in high dimensions, but is intrinsically low-dimensional in some sense. In the second part of the talk, instead of taking sort of a global view on data, I would like to take a multiscale view. Instead of looking at all the data all at once and try to understand it as a whole, I would like to find a way of dividing the data in different pieces in a sort of divide and conquer way and analyze the data at different pieces at different scales. And this will lead to novel algorithms that solve problems which have been open for quite a while. For example, the so-called problem of dictionary learning in signal processing, at least in a certain setting. And I will also be discussing the problem of learning not just sort of good representations for data, but also full probabilistic models for the data that allow us to understand the statistics of the data, generate even new data points that are nearly undistinguishable from the ones that we've seen in the past. And then in part 3, if I ever get there, I would like to briefly talk about some recent work where instead of learning certain geometric properties of the data, we learn properties of dynamical systems, also high dimensional and stochastic. So as a sort of motivation for most of the talk is the following consideration. Data often comes to us in high dimensions. The simplest model of all that one can consider is that data is being sampled from some probability distribution, sampled in a independent fashion. Every sample is an independent draw from all the others. And this probability distribution lives in RD. So capital D is capital, it's large. It's the dimension of the state space of the molecule. It could be the number of words in the English dictionary that are being used to transform a text document in a high dimensional vector. It could be the number of pixels in an image, and so on. And understanding the data ultimately corresponds to understanding the probability measure mu. And this is intrinsically hard in high dimensions. If we have a one-dimensional probability distribution, we can very easily learn about this probability distribution. Let's normalize it so that it takes, you have a random variable that takes value in 0, 1, and it's one-dimensional. You just want to construct bins in order to approximate the distribution of that random variable. And if you want to get accuracy epsilon in estimating your probability distribution, and your probability distribution has a nice density, say Lipschitz, then you could construct your bins to have width epsilon, and you're going to have in the interval 0, 1 about 1 over epsilon such bins. And you want to populate those bins, so you have to have at least order 1 points in each of the bins. It turns out that you need more if you want accuracy epsilon with high probability. You will need about 1 over epsilon squared, but let's gloss over that. In every bin, you want to get at least a few points, and so you need about order 1 over epsilon points in order to build a histogram at all. With the hope of being about epsilon accurate. Well, if you try to play the same game in d dimensions, immediately the curse of dimensionality kicks in, because if your random variable is taking values in the unit cube in d dimensions, and it has a nice Lipschitz distribution in there, then if you divide your d-dimensional unit cube into epsilon bins, you have epsilon to a minus d little cubes of side epsilon. And as soon as epsilon, even if with epsilon moderately large, like 10 to the minus 1, and d, capital D equal to 100, epsilon to minus d is 10 to the 100, which is about 30 orders of magnitude larger than the number of atoms in the universe. So we will never have that much data. And so something has to give, right, if we want to be able to do something about high-dimensional data. And so there are several ways to go around this. I will discuss only one. And I would be happy to discuss other ways to try to defeat the curse of dimensionality. The idea here is to make assumptions about mu and say that mu somehow is special. And the assumptions that we will be making is that mu, in some sense, concentrates around low-dimensional sets. And so this is what I call sort of intrinsically low-dimensional geometric models for data. And the oldest one and simplest one of all is probably principal component analysis, of which many of you, I'm sure, I'm aware. It was introduced by Pearson more than 100 years ago. And it says, well, the simplest geometric model of all, and of course I could talk in statistical terms here, but I'm going to follow geometry. The simplest geometric model of all is saying that the data lies in capital D dimensions, but really it lies on or very close to a low-dimensional plane, maybe a k-dimensional plane. And then how do you find such k-dimensional plane in a robust fashion? Well, you can do the singular value decomposition of the matrix X, decompose it as a product U sigma V transpose with U and V orthonormal, sigma diagonal with the diagonal values called singular values in decreasing order. And then if the data is exactly lying on a k-dimensional plane, it turns out that only k singular values are non-zero. The other ones are exactly 0. And the first k columns of U span that plane. It's important that this construction is robust. Everybody will know how to find a k-dimensional plane in which you have at least k plus 1 points. But if you add noise to the points, this construction is going to generate a decomposition where the first k singular values are large. The other ones are non-zero but small, under suitable conditions of the noise. And again, the first k columns of U would give you a good approximation to the subspace that you're looking for. So people, of course, have used this for a long time, and it's still one of the most popular methods for sort of reducing the dimension, because now you can project your data into the low-dimensional plane, assuming that it's close to it. One of the first applications to machine learning was an attempt to do face recognition in this way. This dates back almost 30 years now, 25 years. So you take pictures of faces, all centered, and there is a mean face, and every singular vector points in the direction of variability of faces in a low-dimensional plane where supposedly all faces lie. And every such vector is a picture of a face, and I put them in one figure. In fact, this is drawn from the paper by Kirby and collaborators. And you see those are the principal components sorted from lowest to highest, so largest singular values to smallest singular value. Now, PCA can be very deceiving too. So let's consider a data set which is even more trivial than the data set of face fronting faces. So let me consider a data set where there is just one white blob on a black background. So one such image is 64 by 64 pixels. It's all black, and it has a white blob in a random position. And sometimes it goes right off the edge. So if you look at this data set, it lies in 64 square dimensions. And you can compute PCA. And each principal vector is an image, 64 by 64. And here they are, from the one corresponding to the largest singular values down to smaller singular values. How do those singular vectors look like? Those are almost exactly, they look like 2D Fourier modes to me, almost exactly, right? They look like 2D Fourier modes. And in fact, that's independent of the blob that I used. I could have used a square blob, I could have used a Gaussian blob, whatever. I would have always gotten principal component vectors, which are just Fourier modes. And I can look at the singular values, and that's what's plotted below there. So as a function of the index I, I'm plotting the singular value that I get from the singular value decomposition of the data set. And that's how they look like. They decrease. They are in log 10 scale. The vertical axis is in log 10 scale. They decrease kind of slowly. And I claim this is very disappointing, because if you think about this data set, let's go back here. This data set is a data set in 64 square dimensions. And it's clearly a two-dimensional manifold, because every point is completely determined by the center of that blob, right? So here is a parameterization for the data set, which is actually how it is being generated. You draw a XY position in the square, and then you draw a Y blob, and you produce a picture in 64 square dimensions. So this is a two-dimensional manifold with a global parameterization given by the unit square. The maps that tells you the position of this circle. So this is a two-dimensional manifold, but it's whirling around in many dimensions in the 64 square dimensional space, and the singular values and the PCA don't capture this data set well at all. And so people realize this, maybe not through this example, but through other examples, and so they try to generalize this simple geometric model to more complicated models. For example, instead of using a flat plane, well, maybe you can use a low-dimensional manifold. Or maybe instead of using just one plane, you can use multiple planes. And already here we're coming to problems that we're studying in earnest, maybe starting 15 years ago. Maybe some people were looking at this type of problems with manifolds and multiple planes 20 years ago. And there are still many research problems in these directions. Before I discuss some of that, I would like to ask a very basic question. Before applying any of these methods, one should make sure that the data is intrinsically low-dimensional. Otherwise, none of this is going to be possible. I cannot fit a low-dimensional manifold to data which is not intrinsically low-dimensional. And so let me open a short discussion about that. So suppose we have our measure mu. Points are being drawn from the measure mu. And what we're seeing are those points, or maybe points perturbed by noise. So maybe what we're seeing are actually not samples from mu, but samples from mu corrupted by noise, say Gaussian noise. And the noise is always in the high dimensional space, because think of each point being a picture. Well, every pixel is going to have noise in it, so every coordinate is going to contain noise. I would like to decide whether the data is intrinsically low dimensional. And this problem has been considered by many people in many different fields for a long time. and still we were unsatisfied with the solutions proposed. And we proposed a new one. First of all, we made the case that the problem of deciding whether the data is low dimensional is really a multiscale problem. You cannot talk about, in most settings, you cannot really talk about one intrinsic dimension for the data. You can talk about one intrinsic dimension around a certain point at a certain scale. And so the problem is intrinsically multiscale. Otherwise, it's completely opposed. And what we do is the following. So let me go by picture. So the setup, our assumptions about the data is going to be that there is some low-dimensional manifold M, where the probability measure is supported. So the data is truly low-dimensional. Unfortunately, we don't know M, and we don't even see points sampled from M. Our points are perturbed by high-dimensional noise. So the green curve is the manifold M. But what we see are points which are not on M because the noise has pushed them out of M. You know, the noise is high-dimensional, M is low-dimensional, so the points fly off M in the high-dimensional space. We're going to do the following. We pick a point Z, which I've drawn on the manifold. And we look at the ball of radius R. And we look at the points inside the ball. And we compute PCA. And we look at the singular values. And then we change the radius of the ball. And we look at how the singular values change as the radius of the ball changes. What is going to happen? Well, I pick my point Z. I look in a small ball. Oh, let me tell you first what the right tube is like. So when you look at high-dimensional noise, and this is going to be a sort of blessing of dimensionality, some statistics of the noise are are very deterministic. For example, if you ask, I draw a random Gaussian vector in d dimensions, what's the norm of that vector? Well, the norm of the vector in expectation is about the square root of a dimension. But it's not just in expectation. It's going to be really close to the square root of a dimension almost all the time. And so what happens to the points from the manifold when you add noise is that they fly off the manifold, but they concentrate in a tube around that manifold. A tube which has a radius, which is characteristic, it's about the standard deviation of the noise times square root of a dimension in the case of Gaussian noise. So if we pick a point Z and a small ball around Z, if the ball has a small radius, almost no point is going to be in that ball because all the points have flown off. And so that ball is going to be empty. If we pick a largest radius, then all of a sudden, we hit the radius of that tube, and we're going to see a lot of points. We do principal components, we find a covariance matrix, but that's not interesting either, because that's just the covariance matrix of the noise. And so we're going to see a lot of large singular values that don't tell us anything about M. If we take an every larger ball, and we look at the singular vectors and the singular values in that ball, now we're going to see something, because this ball has a radius which is larger than the scale of the noise. And so some directions, the green directions, are going to grow linearly with the size of the ball, and the corresponding singular vectors are going to be approximately tangent vectors to the manifold, while all the other singular vectors and the corresponding singular values are sort of stuck and measuring the noise. And so they're not going to grow with the radius R. And if we keep growing the radius R, then we're in trouble again, because this ball is going to include pieces of a manifold which are far from Z, and our singular values and singular vectors are going just to measure things that we're not interested in. So let me do a very trivial example of what this algorithm does on a trivial set. Let me pick an n-dimensional sphere. I put the n-dimensional sphere inside R100. That's the 100 there. I sample 1,000 points uniformly random from the sphere, and there is no noise. That's the 0 there. And then as a function of the radius, I plot the singular values of a set of the covariance matrix of the points in a ball of radius R around, say, the North Pole. So this is how the singular values behave. When R is very small, they're all spread out between 0 and 0.35, which is related to D. And as R increases, we see that they behave very differently. 9 singular values grow in a certain way. The 10th one grows in a different way. Those 9 ones are the ones that are capturing the approximate tangent space of the manifold. And the 10th one is the one measuring the only curvature of the sphere. And then as R grows again, all those 10 singular values are pretty much equal. We're looking at our sphere from far away. We can't tell whether it's a 9-dimensional sphere or a 10-dimensional ball. We can't tell whether it's empty or not. And so all the singular values are large again. So there is a very specific range of scales where we can decide that the sphere is 9-dimensional. So I call those the tangent singular values, the curvature singular values. Now what happens when, And this example might seem completely trivial. Let me make one observation. The sphere is 9-dimensional. It lives naturally in R10, not really in R100, right? It fits inside R10. And I've sampled 1,000 points. Well, in R10, there are 2 to the 10 orthons. 2 to the 10 is 1,024. So I'm sampling about 1 point per orthon. And I'm telling you that just with 1 sample per orthon, more or less, I can clearly see that this is a 9-dimensional sphere, and I can even see the curvature. Somebody told me that before I ran these experiments. I don't know. I would have written the code and tested because I wouldn't have believed it immediately. Oh, yes, sorry. So the horizontal axis is R. It's the radius. It's the radius of the ball that I'm growing around a point Z in the manifold, say the north ball. And the y-axis are the eigenvalues of the covariance matrix of the points in a ball of radius R centered at the north ball. So when at small scale, I'm going to see roughly, all these singular values are about the same. I can't tell that the sphere is 9-dimensional. But as they grow, 9 singular vectors are going to see the tangent space, and the 10th one is going to see the curvature direction. And the singular value in the first 9 are going to see the growth of the covariance matrix in the tangent direction, and the 10th one sees the growth in the normal direction. And these 2 growth rates are significantly different. That's essentially as a function of R. Yes? OK, so there are several small lies in my talks. It's our test to discover them. So I pick one Z. I should take 1 point and do this calculation and show a plot. What I'm showing here, actually, there are black lines and blue lines. So I took all the 1,000 points, and I did an average. That's the black line. And the blue line is the standard deviation. So the blue line is really the expected value over the empirical expected value over those points. And the standard deviation bars are really tightly concentrated around those expectations. I don't have a plot for 1 point. I usually show it. But since this is a sort of small detour, I didn't today. So, and this is with 1 point per orthon. OK? So now let's add noise. So I'm going to add Gaussian noise with standard deviation 0.1 in each direction. How big is that noise? Well, the length of the noise is actually about 1, because the length, in fact, you can compute the expected value of the length square of that noise very simply. It's just the variance in each direction times the number of directions. So it's 0.1 squared times 100, which is 1. So we are on the 9-dimensional sphere. We sample about 1 point per orthon, and we move it in a random direction by 1, which is also the radius of the sphere. So this noise is large. And nevertheless, here is the plot of the multiscale singular values. As a function of R, we look at how the singular values in average over the points on the sphere looks like in a ball of radius R. And now the range of R is pretty much starts at the same point as it did before. So when R is small, nobody's there. The ball of radius R is empty because points have gone away in outer space. But then, when R is about 1.42, we get a lot of singular values. We see the noise. And then for even larger values of R, we see again a deformed version of what we had before. We see 9 singular values that detect that we are on a 9-dimensional sphere, a 10th singular value which measures curvatures, and all the other singular values converge to sigma. Not sigma square root of d, which is what determines the length of the noise, but just sigma, which is the 1-dimensional size of the noise, the 1-dimensional standard deviation. All of this is provable, that this happens in generality. The sphere is no special case. And what we proved is that this is true with noise, and the number of samples that we need in order to get a plot that looks like this is linear in the intrinsic dimension of the manifold. So we need very few samples in order to make these decisions about what the intrinsic dimension is. Previous algorithms depended exponentially in the intrinsic dimension. So you needed 2 to the k points, where k is the intrinsic dimension, in order to make an assertion about what the intrinsic dimension is. We only need order linear in the intrinsic dimension of the manifold. All right. So if we go back, for example, to our trivial data set of blobs, and we do multiscale SVD as a function of the radius. I apologize, I forgot to write R at the bottom there. So as a function of I picked a point, a ball of radius R. As a function of R, I show the singular values. And the data set is clearly 2D. There are 2 singular values growing linearly. There are about 3 that grow quadratically and perhaps more. So those are the curvature of this manifold in 64 square dimensions. But we can clearly see that it's a 2-dimensional manifold. We apply this also to face recognition in an unsupervised way. We use this to say, if you look at a picture of a face and you look around that by doing multiscale SVD, can you capture which are the faces of the same person or not based on linear relationships? I'm not going to go into detail of this unless you ask me to. But what we apply this to, and I want to talk about this, is molecular dynamics. So there we ask, well, suppose somebody gives us long trajectories for molecular dynamics, and they lie in a very high-dimensional space. How high-dimensional really are these trajectories? Do they, do they span most of the ambient space, or they actually concentrate in near low-dimensional sets? So we picked this is in collaboration with Cecilia Clementi and their group in the chemistry department at Rice. So they ran for us long simulations of alanine dipeptide, a very really tiny peptide with only 2 essential degrees of freedom, according to the physical chemist. There are 2 dihedral angles that determine, in some sense, the dynamics of the molecule. And then we ran it also on larger molecules. And so so this molecule has 12 atoms after you take care of the hydrogen atoms and so on. And it lives in 36 dimensions, 3 times 12. And you cannot look at things in 36 dimensions, so you project everything on the 2 dihedral angles recommended by the physical chemists. And you get what are called free energy landscapes. Essentially, the color here represents what is called the free energy. The smaller the free energy, the more likely you are to find a molecule in the state. The larger the free energy, the less likely you are to find a molecule in that state. And so you see that in this landscape, there are 2 blue regions. These are regions where the molecule spends a lot of time. And then there are mountain peaks that you have to climb in order to go from one of those regions to the other. So these are metastable states and rare events who corresponds to climbing up a mountain and falling into another metastable state. Well, so we can ask, if we look near a transition region, for example, up here, that's a transition up to a mountain between 2 different metastable states, we can go in that part of state space and ask, what's the intrinsic dimension of the trajectories that we've seen? And the intrinsic dimension is very low. That's representing the plot up there to the right. The intrinsic dimension is probably 1 or 2 or at most 3. That's again a plot of these multiscale singular values centered around this point. And that says that there are essentially 2 or 3 degrees of freedom in the molecule that govern the transition between the 2 metastable states, at least around that point. If we go near a minimum of a local minimum of the free energy, where the molecule spends a lot of time, there are many more vibrational modes. And if you look at how the singular value, multiscale singular values behave around that point, well, you find that there are many more large ones, but not many, many more. There are maybe, depending on how you want to interpret that plot, maybe 4 or 5. And the rest are fluctuations which are sort of, that are smaller. And so this allowed us to decide at which scale and in which intrinsic dimension we should try to approximate these dynamical systems. They live in 36 dimensions, but for example, near a transition, we should be able to project them down to 2, 3 dimensions, write down 2, 3 equations instead of 36, and hopefully get accurate results. So let me talk briefly about finding coordinates for these manifolds, now that we can test whether the data is intrinsically low-dimensional or not. So this is sometimes called manifold learning, and by different people mean different things by this name. So the idea is the following, or at least one way of formulating the problem is the following. You have a domain in Rk, in the case of the pictures of blobs, that could have been the unit square. And you have a map that takes that, and K is our intrinsic dimension. It's our parameter space. And then you have a map from the parameter space up to high dimensions, R capital D. And the data that we're seeing, xi, is phi of pi. Pi is in parameter space, the unit square. And the xi's are images of those parameters. So the xi's would be the 64 by 64 pictures of blobs. They're high dimensional. And the pi is the x and y of the center of the blob, for example. And so given a bunch of xi's, x1, xn, we would like to find the corresponding pi's and an approximation to the map phi, or maybe phi inverse. And so one of the most cited papers that really started the manifold learning field in machine learning is the ISOMAP paper by Tenenbaum, De Silva, and Langford back in 2000. And essentially they say, well, suppose there is really a low-dimensional manifold, which is globally flat. And so the map phi is, in their setting, is an isometry between a convex domain in Rk to Rd. Then they have an algorithm that if it sees enough points x1, xn, it reconstructs an approximation to phi inverse. So an embedding from a map from high dimensions to low dimensions, which is close to phi inverse. So many other people have worked on similar problems. Dono and Grimes removed the assumption in ISOMAP that required the domain omega to be convex. Of course, phi still needs to be an isometry, a global isometry. So that's saying that the manifold that you're looking at is globally flat, which is a very restrictive assumption. And so, and there's been a lot of other work. I wanted to mention some of the work that I did some time ago with Kaufman and Lafon and others, which is based on harmonic analysis on graphs, and how that relates to this problem. So the construction is the following. You start with data in Rd, and we're going to connect each data point to nearby data points with some weights. So pick the weights, for example, to be e to the minus distance between the points squared over sigma. So every data point is connected to nearby data points, or at least strongly to nearby data points and not strongly to far away data points. You might truncate the Gaussian if you so wish it. And you get a weighted graph where the vertices are the points, and you get edges between the points with a weight. The larger the weight, the closer the points. On a weighted graph, probably the most canonical operator that you can construct is the random walk process, the one associated with the random walk. So the random walk is a process on the graph, and I need to tell you what's the probability of jumping from a vertex of the graph, xi, to another vertex, xj. Well, I would like that to be proportional to the similarity, wij. Well, I am going to choose my constant of proportionality so that I get a stochastic matrix. And so that constant of proportionality turns out to be just the degree of a vertex, which is the sum of the weights of the edges that hit that vertex. And so if you put all the weights in a matrix W, n by n, where n is the number of points, you normalize it by pre-multiplying by the inverse of a degree matrix, a diagonal matrix with the degrees on the diagonal. And you get a matrix P, which is raw stochastic, and it's the matrix of the random walk. And the ij entry is the probability of jumping from xi to xj. This matrix has eigenvalue 1, with multiplicity 1 if the graph is connected. The other eigenvalues are smaller. And you can look at the corresponding eigenvectors, which I can think of as eigenfunctions. Each eigenvector is an n vector, so it's a function on the graph. And people back even in the 50s in computer science, they consider the following map. From every vertex on the graph, you map that vertex to an m-dimensional vector obtained by evaluating the first m eigenfunctions at the point x. And so remember, phi1, phi-m are eigenvectors of the random walk, so there are n-dimensional vectors. And x is a vertex, so it's one of the entries, corresponds to one of these entries in these vectors. And so on the right-hand side of that expression, we have m numbers. And well, what does it do to our trivial data set of blobs? Well, it maps it to a square, which was a good choice for the parameter space. If you apply this to a variety of data sets, just to show you some pictures, and these are nothing more than pictures right now, you can take a data set consisting of text documents. These are papers from Science News. We have about 1,000 of them. And we chose about 1,000 words from the English dictionary that appeared in a meaningful way in these documents. And you get a text document, Word document matrix, where every column represents a document as a vector whose kth coordinate is the frequency of the kth word in the dictionary in that document. And here I just use the binary matrix. You can't see anything in these matrices anyways. So it's 0 if the entry ij is 0 if word I does not appear in the jth document, and 1 otherwise. So each document is a vector in about 1,000 dimensions. And you can construct a graph connecting these text documents based on the similarity function that I described before. You can compute eigenvectors and embed that data set from 1,000 dimensions down to 3D. You get a point cloud like this. Every point here is coordinate given by the value of the first 3 eigenvectors of the random walk evaluated at that point. Now, somebody actually read all these articles and categorized them as belonging to math or physics or medicine or astronomy, biology, and so on. And so that's what the color is. The color is not used in computing the map, but it can be superimposed to these representations. And what you see is that different parts in this embedding roughly have different colors. So that you would expect that you should be able to separate automatically these documents in this low-dimensional space. What strikes me is that you see these structures, which are extremely low-dimensional, almost like lines and arcs and so on, from a data set that was coming from 1,000 dimensions. And these are truly not artifacts of the map in the way we're constructing it. There are some exceptions. So for example, the blue points and the yellow points are mixed there. That's anthropology and biology, which arguably are hard to distinguish. You can play the same game on handwritten digits. These are simple images, black and white of handwritten digits. They're 28 by 28, so they live in about 700 dimensions. And you can embed them down in low dimensions. Every point there is one of those images, and they're colored by the value of the corresponding digits. So you can see the zeros, the dark blue ones, the lighter blue ones are probably the 3s, the yellow ones are the 5s, and so on. And if you look into higher eigenfunctions, you see how they get separated. You can do the same thing for molecules. So this molecule had a space which was 36-dimensional. And from the long trajectories of the molecule, you can compute an embedding down to low dimensions. And so the picture on the right, every point there is one configuration of the molecule embedded down to 3D. And we see this sort of weird manifold-like structure, perhaps, where there are denser regions, denser and higher dimensional. Those actually corresponds to these metastable states. And very thin paths connecting those regions, which correspond to the transitions between those metastable states. And the color is actually the angle phi. It turns out that the angle phi is actually related to the top two eigenfunctions that we construct. And so in a certain sense, there is a match with what the physical chemists knew already. So these sort of maps have been used a lot, and I think that the most successful application has been to what is called spectral clustering, which is the problem of finding well-separated parts of data. And let me give you a very simple example. So suppose your data set is a set of points in 2D. In fact, the dimension really doesn't matter. And clearly, there are two clusters in this picture. There are two groups, the guy in the middle and the guys on the periphery. And you would like to be able to separate them. Well, if you see this picture, you would look for a contour which is roughly spherical. But if these points are in high dimensions, how would you parameterize a good cut between these two clusters? Well, you can think that if you run a random walk from B and a random walk from C, the random walkers will meet very often. But if you run a random walk from B and one random walk from A, it will take a very long time before these random walkers actually interact, because it's hard to go from B to A by selecting random edges, because there are so few edges going between the group in the middle and the group on the outside. And this is actually what this diffusion map or eigenmap is really computing. It's related to this probability of random walkers started at different points meeting each other. And so if you start with this data set and you connect every dot and every cross with the nearby dots and crosses, say with the 5 nearest dots and crosses, you get a graph, you get a random walk. If you compute the eigenvectors and you use those as coordinates in the way described before, you get the picture on the right, where every point in the middle, every dot, is on the far right side, and every point with a cross is on the left-hand side. And they're neatly separated by a straight line, the red line over there, which corresponds essentially to the set of vertices where the first eigenvector of the random walk changes sign. And that red line, if we put it back through the same map, it will correspond to roughly a circular contour. But this map didn't know anything about circular contours or anything at all. It only knew the adjacency matrix of that graph. And so it's really useful for splitting up parts of data sets which don't communicate very much with each other, regardless of their shape. All right. So by now, we know much more about these maps. And theorems have been proved about when they're good, when they're not, and how good they are in a quantifiable way. We've used these maps a lot for studying high-dimensional dynamical systems, in particular for molecular dynamics. So let me go back to this example where we take a small peptide and we produce a low-dimensional embedding of that. How good is that low-dimensional embedding? Is it telling us something about the geometry of the dynamics of the molecule? And it turns out that the answer is yes. So one has to be a little bit careful. So one can write down highly approximate equations for molecular dynamics, which take the form of diffusions, diffusions in potential wells, in energy potential wells. And if you construct the graph in a slightly smarter way than the way that I described before, you can promise that the random walk that you construct on a graph that comes from long trajectories of molecular dynamics actually corresponds to the generator or the continuous PDE that describes the evolution of the molecule in continuous time and space. And so if you have that approximation, then actually the eigenfunctions that you are constructing on the graph approximate the eigenfunctions of that operator. And those eigenfunctions contain a lot of information about metastable states and transitions between those metastable states. And so together with Cecilia Clementine and the group at Rice, we experimented with several molecules where we showed that when you can not only get, by using eigenfunctions of these random walks, you can get a good dimension reduction for your system to the point that you can reduce the whole molecule down to a 1 or 2-dimensional dynamical system, but that this reduction is quantitatively accurate in the sense that if you reduce it to 2 dimensions and then you run a diffusion in 2 dimensions, the rates between the metastable states of that 2-dimensional diffusion are pretty close to the transition rates of the 36-dimensional diffusion that was modeled in the molecular dynamics. So we did this even for molecules where people claimed that there were no dimension reduction possible. So this is a larger molecule that has an unfolded and a folded state. And again, our first coordinate takes care of parameterizing that folding. And we ran it for molecules. This is a polymer that has to go through a nanotube. And again, completely automatically, just by long trajectories of the dynamics, by constructing this random walk in a special way, we can derive coordinates which are good reaction coordinates for this data. So what have we done essentially so far is saying, well, you can look at the data large, build global coordinates, check if the intrinsic dimension is low, and you can use those coordinates in the context of dynamical systems to get a reduction of the system, which is quantitatively correct also in a dynamical system sense. What I wanted to tell in the remaining minutes is how to generalize this to a full multiscale analysis of data set and how to construct probabilistic models for the data. So I'm going to say 2 problems. I'm going to talk at least about the first one. The first one is vaguely stated for the moment. It's going to be better stated in the next slide. Is the following. So we have our data points sampled from some probability measure mu in RD. And I would like to construct an efficient representation for the data, for example, for compressing it, but later on for statistical inference. So I would like to construct a map from our data to d of x, a transformation of that data, where d of x is awfully lower dimensional or requires fewer bits to encode in my data points. And then there is problem 2. I actually don't want to just approximate well my data and compress it, but I would like to be able to approximate the probabilities distribution generating the data, which is typically high dimensional. And I would like to do this with fast algorithms. Theoretical guarantees, how many data points do I need to see in order to approximate the data well with a certain accuracy. And I would like to do this in a way that depends uniquely on the intrinsic dimension of the data so that we're not cursed by the ambient dimensionality. So let me talk about the first problem. So one first attempt at formalizing the problem might be the following. We see n data points, x1 to xn. We would like to construct what is called a dictionary, phi, which is just a matrix, d by m. Every column is a vector in Rd, a dictionary element, such that every one of the data points is both well approximated by a linear combination of my dictionary elements. That's phi times alpha I. Alpha I is a vector of coefficients for xi, so that phi times alpha I is close to xi. But I also want a parsimonious representation, so I'm going to ask that many of the coordinates of alpha I, sorry, it's alpha I, not ai, are 0. So the 0 norm of alpha I is the number of non-zero coefficients in alpha I. And sparsity has had a prominent role in signal processing and statistical inference in the past 7-8 years. So the problem stated in this way is meaningless because there are many parameters here. There is m, the size of a dictionary. There is epsilon, the accuracy. And there is k, the sparsity parameter. And you can get paradoxical statements. For example, I could choose my dictionary phi to be equal to the set of my data points. And clearly, I'm going to approximate my data points really well and in a very sparse way. Every data point has only one non-zero coefficient, the one on the element of a dictionary corresponding to the data point itself. So what is interesting is, in fact, getting accuracy and sparsity on new data points that you're going to see tomorrow. So you have your database today with n points. You want an algorithm that constructs a dictionary, which is going to work well in terms of accuracy and sparsity on future data points, sampled from the same distribution mu that generated the data points xi. Plus, you would like to understand the relationships between the size of a dictionary, the accuracy, and the sparsity level. Of course, in harmonic analysis, we've done this by hand for many years. We would like now to have an algorithm that does this from data automatically. A lot of work has been done. Essentially, a lot of work has been based on the idea that you write down what you want, you get an optimization problem, and you optimize. And you get optimization problems which are in the form below, where you take your data x, you stack it in a big matrix, and you have unknowns, which are the dictionary phi and the coefficients alpha, and you want to minimize a functional which is in the form x minus phi alpha. If that is small, then the data is well approximated by linear combinations of a dictionary. And then you want the alphas to be sparse, and so you add a second term, which is small when alpha contains a lot of zero entries. That 1-1 norm is not quite a standard notation. It's the sum of the absolute values of the entries of the matrix alpha. These problems are non-convex and very hard to optimize. But a lot of people have worked on this, and with some success. Let me now talk about the relationship with quantization. Let me tell you what we did. This is joint work with Nystrom and States-Minsker. So we made the following assumption about the data. And this is actually the first time that we connect this problem to some geometry. We say, well, suppose the data lies on a manifold M. Well, we don't want to make that assumption quite. We want to be robust with respect to noise, but also with respect to the fact that, the manifold might not be smooth. So the assumption that we're going to make is that the data is in a tube around a manifold M. It could be that the data was on the manifold M and we observe data plus noise, or it might be that the manifold model is wrong and the data does not lie on a smooth manifold, it lies close to it in some sense, but we cannot make more precise. And the width of this tube is going to be called sigma. Then we can prove the following theorem. So sigma is the radius of a tube, and we're going to fix an accuracy epsilon, larger than that sigma. Then suppose that in our database today, we have a number of points which is larger than that accuracy that we wish to get, to -1 plus d over 2. D, the small d there, is the intrinsic dimension of the manifold. Okay, so we have our points in our database today. Those have been sampled from some probability measure pi. And we are going to give you an algorithm that, given these n data points, is going to output a dictionary, which I call phi hat. It's going to produce a map from high dimensions to the dictionary, to coefficients onto the dictionary, and an inverse for that map, such that with high probability, over the samples that you have in your database today, the following things happen. Your dictionary is as a size that we can upper bound. Your dictionary is no larger than epsilon to the minus d over 2. The encoding onto that dictionary, so if you take a point, in fact, any point from the probability distribution, and you encode it with the map that we give you onto the dictionary, you're going to get a vector which is d plus 1 sparse, where d is the intrinsic dimension of the manifold. And moreover, the accuracy that you wish for, you actually get, in the sense that when you're going to sample from the probability measure pi in the future, and you have your x, and you compare it with encoding x in your dictionary, that could lead to loss of information because we are getting a very sparse representation, for example, and you decode, the error that you're going to incur is never larger than epsilon. So this establishes the relationships between how many points you need to get a certain accuracy with a dictionary of a certain size and with a given sparsity level. And the sparsity level is extreme because you're in a d-dimensional manifold, so you're going to need at least d numbers in order to encode where you are on it. Moreover, we can tell you how long the algorithm is going to take. The algorithm is scaling for constructing phi, scales like epsilon to the -1 minus 2 over d, which is n, if you take the equality up there. It scales linearly in the ambient dimension capital D, because we're looking at the data matrix, and the data matrix has size d times n. It scales quadratically in the intrinsic dimension, and it has an exponential dependency in the intrinsic dimension. You have a universal constant capital C to the d. So that's like 4 to the d. So scales linearly in the matrix size with a constant which is exponential in the intrinsic dimension. The encoding map is extremely fast. It's the cost of a projection from d dimensions to small d dimensions. And the decoding map is even faster. And so there is a fast transform onto this dictionary. Yes? Yes, and in the paper, we meticulously track all those dependencies. And all the only parameters that enter in these constants are dependent on two things, sigma and tau, which is the reach of the manifold. It's sort of the radius of the largest tube around the manifold that doesn't self-intersect. And these dependencies of the constants in terms of those two only parameters are completely spelled out in the paper, literally with all the numbers and the dependencies. So if you write this in terms of n, this is saying that as you get more and more points in your database, you get better and better approximations. And we think that nobody can beat this algorithm. And maybe in the 1 minute left, I wanted to give you an idea of what the algorithm is. And this is joint work with Guanglan Cheng and Bill Allard. So the idea is the following. You start with your data, and you're going to divide it in a multiscale fashion. So you divide it, for the sake of this presentation, so you divide it into 2 pieces. Each piece gets divided into 2 pieces, and so on. And we construct these pieces by using a very specific algorithm, which is a small variation of the cover tree algorithm by Langford and others back in 2002 or 6. I'm sorry, I forgot the correct year. So we have divided the data into multiple pieces. In each of the pieces, we're going to do the trivial thing. We're going to do low rank SVD. Okay, so we divide the data into pieces. Each of the pieces we call CJK. The pieces are scale J, have the J fixed, and K indexes those pieces. They're like dyadic cubes at scale J. And in each of these pieces, we're going to do PCA. And we're going to do low rank PCA because we know that we are on a d-dimensional manifold, and we know how to compute d because we know how to estimate the intrinsic dimension. And so we project the data locally on a d-dimensional space. And so in each of those nodes of a tree, you have a low rank approximation to your data. But now if you look at one node, you have a low rank approximation, but you have a low rank approximation also the parent node. Well, how are they different? If there is any smoothness in the data locally, then these two low rank approximations shouldn't be very different. So I shouldn't be encoding them separately. I should really talk about encoding the difference between the low rank approximation in one scale and the one of the children. And so that's what we do in the first step. These are sort of like wavelets for those of you that are familiar with wavelet theory. They encode the difference in one scale to another, but in a way which is very different from how wavelets do that. And so when we do that, in the end, we get a sort of approximation of data by many planes and multiple scales and locations. This is sort of the picture trying to capture that. And that leads to really interesting encoding for data. And it eventually leads to this sort of dictionary learning, where the dictionary elements are the coordinates of these low-dimensional planes. So if you have a low-dimensional manifold, you can encode it. So this is a very simple 2-dimensional manifold in 100D plus noise. You can encode it by a table of numbers, which are the coefficients of the points on this manifold in terms of this multiscale family of planes. And in that table there, up to the right, there is a lot of white. White corresponds to 0. So the table is sparse. So the encoding of this manifold is sparse. And we can also control the approximation rate. We can run this on different data sets. So these are, for example, the simple data set of handwritten digits. The one that we looked at before, you get a very sparse table. And one picture that I want to comment on is this picture down here. So there, I represent all the planes that we have constructed, going from the coarse scale to the finer scale. And I color each plane by its dimension. So these planes live in about 700 dimensions, which is where the data lies. But the dimension of these planes is really small. It's between 1 and 5. And so you have this hierarchy of very low-rank planes scattered in 800 dimensions, but well organized in this hierarchical factorization. You can do this in, say, 600 times 400 dimensions for pictures of faces from the Yale database. You get multiscale approximations. And again, if you look at the dimension of the planes involved, they're all between 1 and 15. Most of them are between 1 and 8. So these sort of local multiscale low-rank factorizations can go a long way into obtaining efficient representations for data. So we have been using these for images and studying image patches. The world of image patches is often low-dimensional. Let me not talk about that. We got new fast transforms for images, but we are exploiting now for computer vision type of applications. We have extended this construction to matrix spaces. And why we really care about this? Because we care about this because the distance between data points, the natural distance between data points often is very far from being Euclidean. Think about comparing two pieces of image. You don't want to do this with respect to the Euclidean distance. You want to do this, for example, you want to do this modulo translations or rotations and small deformations. Well, we now have a way of doing this, where we define a metric which is invariant under a certain set of invariances that you would like to have, and we get a dictionary which has all those invariances built in. So we're now thinking of these sort of data decompositions as sort of how data should really be stored and used in algorithms. And so we asked how many other algorithms and machine learning tests can be accomplished in this in parsimonious data representation. And so you can do several things. In fact, we think almost everything, because we have guarantees on the accuracy of our representation, so the information is there. One of the things that we have done very recently is we came up with new ways of doing regression and classification, approximation of high-dimensional dynamical systems, but also strange things. For example, how to compute optimal transportation plans between point clouds efficiently. So you might have two data sets, or maybe one data set varying in time, and you're interested in matching these data sets. But maybe the number of points is changing, and you would like a robust way of measuring that. Well, one robust way of doing this is using optimal transportation distances for doing this, except that they're very hard to compute. And we came up with, by using the sort of multiscale decompositions that I discussed, we came up with ways of computing those optimal transportation plans in a multiscale fashion and with control accuracy. And one of the applications that we are considering right now is, and this is still work in the doing with one of my postdocs, Sam Gerber at Duke. So we're applying this to brain imaging, where we have collections of brains with density measured at every point in 3D. And you would like to compare brains. And so people have tried to use diffeomorphisms and so on, and those often lead to very computationally intensive comparisons. And it's not even clear that that's the correct metric to be used. We use our multiscale transportation plans to introduce a metric for comparing brains. And I'm really out of time. My time is up. I want to tell you one thing. We use the same thing for estimating not estimating dictionary that gives us sparse representation for data, but estimating the probability measure that produces the data itself. This is a much harder task. As we said at the very beginning, it's cursed by the dimensionality, but actually you can design algorithms which depend only on the intrinsic dimensionality of the data. And so what I'm showing there are fake pictures of handwritten digits. So you have an algorithm that looks at some pictures. It learns not just a good dictionary, but it learns about the distribution of the coefficients onto that dictionary and produces new pictures. And those are all fake. These are all samples from our probability distribution that approximates the true one. And so here I have more fake pictures of handwritten digits that we produce with our algorithm. Of course, handwritten digits are simple pictures. We would like to scale this up to, for example, faces. Can we generate artificial new pictures of faces just by staring at a lot of pictures of faces? Clearly, we can do this in our mind. I would like to be able to do it algorithmically. We're not there yet. We do have a theory for why we can do this and why we can do this in a way which is dependent uniquely on the intrinsic dimension. So let me skip just to the end of the talk. Clearly, I'm not going to tell you about high-dimensional systems. So let me do that. So some of the things that I'm working on right now. So first of all, a matrix-based version of these multiscale decompositions. It's not hard to construct multiscale trees in matrix spaces. That's done. The hard part is, well, what does it mean to do linear combinations of elements in a matrix space? It doesn't make any sense. And so that's the part that we've given an interpretation to, and we think it's the correct interpretation. And then it turns out that you can solve a lot of different problems, both algorithmic and theoretical, by using this sort of decomposition in matrix spaces. We're very interested in pursuing the study of maps between multiple objects, for example, the maps between brains. So if you have a lot of brains, you measure distances, you get a notion of how elements in your database are related to each other, and that should actually inform which matrix you should be using and how you should be doing learning and predictions on that data set. And wanted to put the last page with my collaborators that appear in this work. And thank you for your attention. And if you have more questions than the ones you already asked, I'm very happy to answer them.